Today we're going to talk about coordinate systems. We need coordinate systems in order to do algebraic calculations in a vector space. To create a coordinate system in a vector space, we need to have a basis. So let V be a vector space with a basis B, which is V1 through Vn. As an example, let us consider the case when V is two-dimensional, so that is a plane. And so suppose we have a basis in this plane. For some problems where we need to compute angles and distances, we would prefer to work with an orthogonal basis. But for other problems, non-orthogonal basis may be more convenient. So once we have a basis, then we can create coordinate axis, and then for each vector in this vector space, we can compute coordinates of a vector with respect to a given basis. We point out that any vector V in this vector space V may be written as a linear combination of basis vectors in a unique way. So we can write V as a linear combination C1V1 plus C2V2 plus CNVN. And these coefficients in this linear combination, C1, C2, Cn, are uniquely determined by a vector V because of linear independence of our basis vectors. We call the n-tuple of coefficients so this column C1, C2, Cn, the coordinate vector of V in basis B. And we're going to denote it as V with the subscript B. So VB will be the coordinate vector of a given vector V with respect to a basis B. And we obtain it by decomposing the given vector as a linear combination of basis vectors. In this diagram, we find the coordinates of a given vector using parallelogram rule. So we draw two lines through the endpoint of V that are parallel to our coordinate axis. And then here we have a multiple of V1, so we call it C1, V1. And here we have a multiple of V2, which we call C2, V2. And then the coordinates of this vector in the given basis will be a pair C1, C2. Let us consider some examples. So suppose U be the space of quadratic polynomials. So ax squared plus bx plus c. Right? So this is a subspace inside the R of x. And here we choose a basis B. So the space is three-dimensional and it's spanned by monomials x squared, x, and 1. So let us fix this as our basis. And let's consider a vector in this space, which is a polynomial 3x squared plus 5x minus 7. Then we view this as a linear combination of basis vectors. So this is 3 times x squared plus 5 times x plus negative 7 times 1. Then the coordinates of this vector with respect to the given basis will be a column vector 3, 5, negative 7. So this is coordinates of V with respect to basis B. So in this context, the vector itself is a polynomial, and the coordinate vector of V is the column vector. As our second example, let us take a vector space of 2 by 2 matrices over real numbers with basis B, which consists of the following matrix: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Now, if we take as a vector in this vector space the following matrix: 3, 2, minus 5, 6, then we decompose this matrix as a linear combination of basis vectors. So this will be 3 times the matrix 1, 0, 0, 0, plus 2 times the matrix 0, 1, 0, 0, plus negative 5 times the matrix 0, 0, 1, 0, and plus 6 times the matrix 0, 0, 0, 1. And as a result, we see that the coordinates of this vector with respect to this basis is a column vector with 4 components. So this will be 3, 2, negative 5, and 6. It often happens that a vector space does not come with a natural basis. In these situations, we have to choose a basis ourselves in order to create coordinate systems. We encounter this situation often when we deal with subspaces. So let us look at our next example. So let U be a subspace in R3 given by equation x plus y plus z is equal to 0. In this example, U is a plane in 3-dimensional space, and in order to construct a coordinate system inside U, we need to choose 2 non-proportional vectors in this plane. For this particular example, so we can choose the following 2 vectors. We can take V1 to be 1, minus 1, 0, and V2 to be the vector 0, 1, negative 1. Now let us take a vector U in this subspace. So let's choose the following vector: 5, 2, negative 7. So here the sum of components is equal to 0. So this means that this vector belongs to our plane. And we want to compute the coordinates of this vector with respect to this basis. In order to do this, we want to decompose the given vector U as a linear combination of basis vectors. So we want to write it as x1 times 1 minus 1, 0, plus x2 times 0, 1, negative 1. In this particular case, it's easy to see how this can be done. So if we take 5 times the first basis vector plus 7 times the second basis vector, then we can easily see that this linear combination is equal to our vector U. This tells us that the coordinate vector of U with respect to basis B is the column vector 5, 7. If we had a more complicated basis, then in order to find the coordinate vector UB, which is x1 and x2, what we need to do is we need to solve this vector equation. And this is equivalent to solving the following system of linear equations. So 1, -1, 0, 0, 1, -1, and with the right-hand side vector 5, 2, 7. If we solve the system of linear equations with this augmented matrix, then we're going to get a unique solution. x1 is equal to 5 and x2 is equal to 7. Let us ask ourselves the following question. So let V be an n-dimensional vector space with basis B, which is V1 through Vn. What are the coordinates vectors of the basis vectors? So in other words, so for example, if we take the basis vector V1, what will be the coordinate vector of V1 with respect to the same basis B? In order to answer this question, what we have to do is we have to decompose V1 as a linear combination of basis vectors. And it's clear how to do this. So it's 1 times V1 plus 0 times V2 plus all other coefficients, we choose 0 as well. And then we see that the coordinate vector of V1 with respect to its own basis will be the column vector 1, 0, 0, 0. And likewise, for the vector V2, its coordinate vector is going to be 0, 1, 0, 0, and so on. And for the last basis vector, we get the column 0, 0, 0, 1. So what this tells us is that when we choose a basis in the vector space and start working with this coordinate system, then essentially we can interpret these basis vectors as the standard basis vectors. This conclusion may be interpreted in the following way. By choosing a basis in the vector space, we construct an isomorphism from Fn to V. This isomorphism sends a column vector C1, C2, Cn into a linear combination of basis vectors C1, V1 plus C2, V2 plus Cn, Vn. And what we see is that under this isomorphism, so the first standard basis vector will go to basis vector V1. And so now we have a correspondence here between basis vectors in the space V and standard basis vectors in the space Fn. And so here is another way to look at this correspondence. So this is implemented by taking coordinates vectors of a given vector with respect to the given basis. The next topic that we would like to discuss is called change of basis matrix. We could have a situation where we have one vector space, but two different bases in this vector space. And these two different bases will create two coordinate systems in the same vector space. And what we want to do is we want to find out how can we recalculate coordinates of vectors from one coordinate system into another coordinate system. For example, consider a situation with the International Space Station. International Space Station has two mission control centers. One is in Houston, and the second one is in the city of Korolev in Russia. And so what we need to do is we need to track the International Space Station from both mission control centers. So what we can do is we can create coordinate systems, say one coordinate system that is associated with Houston, and the second coordinate system, which is associated with Korolev. We choose origins of both coordinate systems at the center of the Earth. Both mission control centers will track the International Space Station in their own coordinate systems. But then, when they need to talk to each other, they need to recalculate from one coordinate system to another coordinate system. So, for example, if we know the position of International Space Station with respect to Houston coordinate system, then we need to be able to recalculate the coordinates of the same point with respect to Korolev coordinate system. Furthermore, so if we are launching a rocket with a supply ship that needs to dock with the International Space Station, then for the docking procedure, we will also need to consider a coordinate system that is associated with the International Space Station and be able now to recalculate between three coordinate systems, of which one of them is even moving. When we need to work simultaneously with two coordinate systems, we adopt the following approach. We take the basis associated with the first coordinate system as a standard basis, and the basis associated with the second coordinate system as a non-standard basis. And now we need to learn how can we recalculate from the standard basis to the non-standard basis. Consider vector space Fn with a standard basis E, which we denote E1, E2, En. So these are the column vectors 1, 0, 0, 0, 0, 1, 0, 0, and so on. And a non-standard basis. So, which means another basis in the same space. So B, which is V1, V2, Vn. Suppose for some vector V, we know what are its coordinates with respect to the basis B. And suppose this will be C1, C2, Cn. Now, question. How can we find the standard coordinates of the same vector? To do this, we recall what's the meaning of the coordinate vector. So if VB has this coordinate vector, so this means that the vector V itself is a linear combination of basis vectors with these coefficients. So it's C1, V1 plus C2, V2 plus Cn, Vn. But then it's clear that in order to get standard coordinates of this vector, what we do is we just take standard coordinates of the first basis vector and multiply it by C1 and just take a linear combination of standard coordinates of these basis vectors. So this linear combination of column vectors can be interpreted as a product of some matrix with the column vector C1, C2, Cn. Now let's figure out what is this matrix. We know that the product of a matrix by a column vector is a linear combination of columns of the given matrix with the coefficients that are given by the vector. So this tells us that the first column in this matrix is V1E. Then the second column will be V2, E, and the last column will be Vn, E. This matrix is called the change of basis matrix. And here is the rule that we use. So to construct the change of basis matrix that will denote C, B to E, place standard coordinates of basis vectors from B as columns. This change of basis matrix serves the following purpose: that for any vector V in Fn, so if we take change of basis matrix B to E and multiply it by the coordinates of a vector V with respect to basis B, so this is what we do here, so this is VB, then the result will be the standard coordinates of the given vector. So this formula says the following, that if we take coordinates of a vector V with respect to basis B and multiply it by a change of basis matrix going from B to E, then the result will be the standard coordinates, or the coordinates with respect to E, of a vector V. And here we have a rule for constructing this change of basis matrix. So let's consider the following example. So consider the following bases in R3. So let's take vector 1, 1, 1, 1, 2, 3, and 0, 5, 2. So then the change of basis matrix from this basis B to the standard basis is obtained by placing the standard coordinates of these basis vectors as columns. So we'll get the matrix 1, 1, 1, 1, 2, 3, and 0, 5, 2. And this matrix will allow us to recalculate from coordinates with respect to basis B into the standard coordinates. Now, what are the properties of the change of basis matrix? Well, first of all, this change of basis matrix is square. And then what we see is that the columns of this matrix are linearly independent. And span Fn. So this is because the columns are vectors from the basis B, and by definition, vectors in a basis are linearly independent and span the space. From here, it follows that the change of basis matrix is invertible, because the previous condition tells us that its reduced row echelon form is the identity matrix. Now, this formula tells us how can we go from coordinates with respect to B to the standard coordinates. It is often interesting to know how to go the other way around, from the standard coordinates of a vector to coordinates of a vector with respect to a non-standard basis B. To do this, we use the opposite change of basis matrix. So we want to write VB as a product of some matrix where we go from E to B by the standard coordinates of a vector E. Now, how can we find this opposite change of basis matrix? Well, we can do this purely algebraically. If we have this relation and this matrix is invertible, then we can multiply both sides by the inverse of this matrix. And then what we get is that C, B to E inverse times the standard coordinates of V. So this should give us the coordinates of V with respect to the basis B. And now comparing these two formulas, so we conclude that the opposite change of basis matrix, where we go from standard basis to basis B, is the inverse of the change of basis matrix from B to E. So as an exercise, find coordinates UB of vector U, which is 5, 1, 5. So here we have this basis, and we have this vector U, and of course these are standard coordinates of a vector. And now we need to find non-standard coordinates of the same vector with respect to this basis. And there are two possible approaches to solving this problem. So the first approach is we can say that UB is equal to change of basis matrix from E to B times the standard coordinates of this vector, which are given. But we don't have this change of basis matrix. We only have a change of basis matrix from B to E. So what we can do is, so we can compute the inverse of this matrix and then multiply the vector UE, so the given vector UE, by the inverse of this change of basis matrix. And the second approach is from this formula, right? So we can say that so UE is C B to E times UB. And so here we have this matrix and we have the right hand side. And so the unknown is the column vector UB. And so what we see is that this is a system of linear equations. So now we treat UBs as the column vector of unknowns, and we just solve this system of linear equations. If we need to calculate a single coordinate vector UB, then the second approach is better. So it's easier to solve one system of linear equations compared to inverting a square matrix. However, if we need to solve these problems on a massive scale, so if we have two coordinate systems and we need to routinely to recalculate from one coordinate system to another coordinate system, then it's better to compute once and for all the inverse matrix, which will be the change of basis matrix from E to B, and then carry out this computation by matrix multiplication. Sometimes we work with coordinate systems that have different origins. So, for example, when we send a supply ship to the International Space Station, then we may be calculating the coordinates of this supply ship in the Houston coordinate system. But when it comes to docking with the International Space Station, we also need to calculate the coordinates of the same supply ship with respect to the coordinate system associated with the International Space Station. And if Houston's coordinate system may be centered at the center of the Earth, so the origin of the second coordinate system may be attached to the International Space Station itself. This brings us to the notion of affine space. So let us consider the following example. So if we need to construct a mathematical model for a flat sheet of paper, then we can use R2 to do this. But for this, we need to take this sheet of paper and create a coordinate system on it. And to create a coordinate system, not only we need to have basis vectors, but we also need to choose an origin. And as it is, so this sheet of paper does not have the origin. So here we need to make two rather arbitrary choices. So first, we need to select the origin on this sheet of paper. And then secondly, choose a basis for our coordinate system. As a set, an affine space is the same as a vector space. only we consider elements of an affine space to be points and not vectors. When we construct coordinate systems on affine spaces, we are allowed to choose different points as origins. As an example, so consider a plane x plus 2y plus 3z is equal to 6 in R3. So this plane W is not a subspace because 0 vector does not belong to W. So this means that this plane is not a vector space. So still, if we need to, we can create a coordinate system on this plane by choosing an arbitrary point of the plane as the origin. This tells us that we cannot treat W as a vector space, but we can still treat it as a affine space. Consider two coordinate systems on an affine space. So standard, that we call E, and non-standard, that we call S. Then say we have one standard coordinate system E, and possibly we have another coordinate system S on the same plane, right? So with possibly different origins, because this is the point of affine space, that we can change the origin of a coordinate system. Now, how can we recalculate coordinates of points from one coordinate system to another coordinate system? So to recalculate from one coordinate system to another, so we use the following formula. So if we have, say, point P on a affine space, then the standard coordinates of this point P will be obtained as some matrix times non-standard coordinates of this point plus some shift vector B. So this vector B represents the shift between the origins of the two coordinate systems. And then this formula also tells us how to do the opposite recalculation. So here, if we know the standard coordinates of the point P, to obtain the non-standard coordinates, so what we do is, well, we move B to the left-hand side and then multiply by C inverse. So it will be C inverse times standard coordinates minus this shift vector B, right? Or, so this will be C inverse times PE minus So the new shift vector will be C inverse times B, or negative C inverse times B. Once we understand well how change of bases works in vector spaces, then going from vector space situation to affine space situation is relatively easy. So what we need to do is we just need to incorporate the shift vectors. The most interesting part will be in this change of bases matrix. And because of this, in this course, we'll focus on change of bases in vector spaces. And then adopting the situation where we need to shift the origin, so it becomes fairly easy. As another illustration of the notion of affine space, so let us discuss the game of set. So the game of set is played with a deck of cards, where the cards look like this. So here are some cards of this deck. So each card in this game has 4 characteristics. So this is shape. And here the shape could be a diamond, could be an oval, or could be a wave. Then we have a number. So we could have 1 object, 2 objects on a card, or 3 objects. Then there is shading, which can be solid, could be striped, or could be empty. And finally, there is color. So it can be red, green, or purple. So, for example, this card, well, it's a diamond. There are 3 of them. So it's striped, and the color is green. And in this deck, there is 1 card for each combination of these characteristics. So we conclude that the number of cards in the deck is 3 to the power 4, which is 81. So because we have 3 options for shape, 3 options for the number, 3 options for the shading, and 3 options for the color. And so the total number of combinations is 3 to the power 4. So how is this game played? So we lay 12 cards out of this deck. And the objective is to find a set. And a set is 3 cards for which each characteristic is either the same for these 3 cards, or all different. Okay, so let's look at an example. Let's take this card, and this card. So here I claim that these 3 cards form a set. Now let us look at the shape. So for the shape, so these 3 cards have the same shape, so they're all waves. Then for numbers, so these 3 cards will all have different numbers. So we have a card with 1, a card with 2, and a card with 3. For shading, again, all of these three cards have the same shading. So they're all striped. And for color, so all colors of these cards are different. So we have red, green, and purple. So this means that these three cards will form a set. This is not the only set that can be formed within these 12 cards. I give you a challenge to find another set here. What we want to do is we want to interpret this game from the point of view of linear algebra. So we can think of each card as a four-component object. So we have one component for shade, one component for number, one component for shape, and one component for color. And each component has three possible values. This suggests that the deck of the game of set may be modeled by taking a field of three elements and then taking the four-dimensional vector space over the Z3. So one issue with this approach is that, so here in this deck, it's not clear what is the origin. And in fact, the proper interpretation of the deck of the game of set is that it's not the vector space over the field Z3, but it's rather the affine space over the field Z3. If we interpret the deck of the game of set as a four-dimensional affine space over the field Z3, then what is a set in this game? Well, it turns out that a set is a line in this affine space. So the game of set now is the following. So we're given 12 points in this four-dimensional affine space, and we need to see which three of these 12 points lie on the same line. So, and indeed, in Z3 to the power 4 as a vector space over Z3, a one-dimensional subspace will contain 3 points, right? So because we have a non-zero vector, and then we can take three multiples of this non-zero vector. So this means that a line in the vector space Z3 to the power 4 consists of 3 points. Likewise, a line in the corresponding affine space will also contain 3 points. And these are the lines that we need to uncover in the game of set. When we started to play the game of set in my family, so I was unsatisfied that there is only one game that you can play with this deck. And I was started to think, so what are other possible games that you can invent and play with the same deck? And here is how mathematics helps you to invent new games. So if we have an affine space, then we can go to a vector space by taking displacement vectors. So if we have 2 points, so A and B are points, then we can create vectors AB. And this also defines for us addition of vectors. So if I have two vectors with the same origin, then I can define their sum. Now, suppose I take these two cards as my points A and B, and this card as a point C. Then what I want to do is I want to find a point D here, such that the vector AB is equal to the vector CD. So I'm thinking about the vector AB as a displacement. Now in this vector we go from red to purple, we go from 1 to 2, we go from diamond to oval, and we go from solid to striped. So this creates cycles. So because if we go from red to purple, then the next we can go to green and then return to red. Then we go to 3 and then we return to 1. Then we go to wave and return to diamond. And then we go to empty and return to solid. So next we take any other card, and then we see how we can apply the same shift to this card. So this card has green, so when we apply the transformation to it, we obtain red. So then here we have 3. When we transform, we get 1. So here we have waves. So when we make this transformation, we get diamond. And so here we have striped. So when we apply this transformation, we get empty. And this gives us the characteristic of the point D such that the vector AB is equal to the vector CD. And now we can see that these 4 cards will form a parallelogram in this affine space. And this suggests that there is one other game that we can play with this deck. So, and I call this game Gram. So lay 9 cards and see which 4 of them form a parallelogram. And you need 9 cards to have a decent probability that you will have a parallelogram among them. So what we see is that the game of set is just a 4-dimensional affine space over the field of 3 elements. And just as in Euclidean geometry, we can introduce vectors as displacement between pairs of points. So here, by taking displacements between 2 cards of the game of set, we can introduce vectors, and we can even go from this affine space to the vector space of vectors that connect pairs of cards in this deck.